Okay, this lecture we're going to talk about what happens when you try to calculate the divergence of functions that blow up or basically go to infinity or negative infinity at a point. And so the learning objective is to understand why you can't simply calculate the divergence of a point where it blows up. Like you can't, for example, at a point charge. Okay, so let's just quickly review. Now we've got two different forms of Gauss's law. Okay, we've got our integral form, which basically looks like this guy. I don't know why I decided to start using capital Q's. And then we also have our differential form, which is what we derived in the last lecture. Both useful depending on what you're trying to do with it. Okay, we're going to apply both of these laws to a just general volume charge distribution. So let's remember what that looks like. That basically says, hey, the electric field at some point R is going to be equal to 1 over 4 pi epsilon naught times the integral of some general, okay, volume charge density evaluated at the position of the source charges divided by our separation vector squared times our r hat, that unit vector that points in the direction of the separation vector, evaluated over the total volume of the source charge, okay? And what I want to do with this volume charge distribution is I'm going to go ahead and calculate the divergence. So let's calculate the divergence. Okay, so when I do that, I'm going to take the dot product with that del operator, but now I'm going to do it on this fancy integral. Okay, when I do that, I can pull that del operator into the integral. And I'm actually just going to end up applying this del operator to this little chunk here, which is the only chunk that actually depends on the position where you are evaluating the electric field. Okay, so I want to just write a little note here that our del operator, this applies to the non-primed coordinates, okay, which is basically just the R ones, right? But not, okay, to our primed ones. Because you're evaluating the divergence where you are measuring the field. All right, that is a lot of writing. Okay, so that is essentially why I could take this del operator and scooch it all the way into this integral where it only applies to these bits, because these are the only bits that depend on the non-primed positions. All right, let's keep moving forward. In order to make writing this a little bit easier, we're just going to look at this bit of the integrand, just the part where the del operator is being applied. So this is still a dot product here to our r hat. I'm getting worse at drawing these r's. This is r hat divided by our separation vector squared. I'm going to rewrite this in this other form, okay, that we learned about in week 1. So this is the same thing as taking the separation vector divided by the magnitude of the separation vector to the third instead of squared. And then I'm going to write out what this actually would be in our Cartesian coordinates. So we got x minus x prime, y minus y prime, z minus z prime. Down here, we got all of that business. Oops. Squared and then taken to the 3/2. Okay, again, we're just putting in what our separation vector actually is here. This 1/2 comes from the fact you have to take the square root to calculate the magnitude, and then you've got the power of 3 up here. All right, let's just look at one component. Really, this is still this part of it is still a vector, but let's just look at this x component. So let's just apply our del operator to the x component, make our life a little bit easier. When you do that, it's kind of a nasty derivative. You're taking the partial derivative with respect to x of this over all of this guy, okay? So I'm just going to be a little bit lazy about writing it, okay? So these blank stuff, that's all that. I just don't want to write it over and over again, okay? So just a lot of the chain rule here. Okay. Nastiness. Okay. So I can simplify that a little bit. In particular, I can simplify this part here. Okay, and I can rewrite this as being 1 over, again, this is going to end up being the magnitude of my separation vector to the third. That's what this term looks like. But now I've got this other term. When I simplify it, I end up getting minus 3 to the x minus x prime squared over the magnitude of my separation vector to the 5th, okay? And the other components in the x and y direction are similar. They look pretty much the same, but you got y's instead of x's. Okay, so what can we do with that? Therefore, if I evaluate the divergence of my electric field, I end up getting something when I sum up all of the partial derivatives in the various directions together. I get something that looks like this. Okay. All right, and again, that's just because we're repeating this bit for all of the different directions. Okay, and we get 3 of these, 1 for each direction. All right, if I look up top here, this is just the magnitude of my separation vector squared. So if I put that all together, I end up getting this kind of thing. Okay. And that equals 0. Huh. Okay, that was a lot of math, but let's just put that in the think about it for a second. Okay, so I calculated the divergence of the electric field of a general volume charge density, and I ended up with 0. That seems a little troubling. Let's try an even simpler case. Let's just try Coulomb's law. That describes the electric field around just a positive or negative charge or some point charge, okay? So this I should be able to understand. It shouldn't have a zero divergence. Okay, so let's do that. I'm going to take the divergence of this field. Okay, when I do that, I can pull out, right, these constants and just apply my del operator to the bit that actually depends on the position where I am evaluating the field. So that's 1 over r hat. Okay, this problem is easier to do in spherical coordinates. That way I can leave this as an r and not replace it with an xyz mess. Okay, so I'm going to look on the back cover of my book and I'm going to look up what del looks like in spherical coordinates. Okay, you don't necessarily have to memorize or derive these things. Sometimes it's okay just to look it up. And when I do that, I'm going to find that just the r component of my del operator looks like this. Okay, so I want to take 1 over r squared times the partial derivative in the r direction times r squared times whatever my vector field is, that component in the r direction. Okay, so this is what I get at the back cover of my book, but I want to apply it to this particular problem up here. Okay, so again, I'm just going to be looking at the r component. So I'm going to have my del operator. And I'm skipping this. I'm just going to look at this little bit here. So I'm going to do 1 over r. Oh, I forgot a squared here. Squared times r hat. Okay, this is my, like my VR here. And when I evaluate that, I get 1 over r partial derivative with respect to r of r squared times the VR component of my function. So that is 1 over r squared. Okay. Obviously, when I do that, this thing is going to go to 1. So I'm going to end up with 1 over r squared times the partial derivative of r of 1. And that's going to give me 0. Okay, whew. That cannot be right. The divergence right at the middle, right at the point of a point charge cannot be 0. We just learned a lot about the divergence. And I pretty much told you it was where flux is created, right? And we know that electric flux is created right at a point charge. Okay, so there's a problem here. There's a math problem, and we need to solve it. What is the source of the problem? Well, the problem is that the electric field, it blows up. It literally goes to infinity. At the location of the point charge. Okay, so it's blowing up, in this case, at r equals 0. Okay. Basically, the mathematics we have to take the divergence can't handle this idea that we have a vector field that is going to infinity at the point where we're trying to calculate the divergence. So we got problems. And we need a mathy trick to solve them. Okay, and that's the subject of the next video.